Welcome, and I shall present some new results which we did in collaboration with Jeffrey Kerling, who is from Dresden, and he will give some GPU programming details after my talk. So let me start with some introductory sentences about brain science. Theoretical and experiments suggest that brain operates near a critical state between sustained activity and inactive phase, which exhibits optimal computational properties. This is one common hypothesis, I would say, in brain science, our beginning point. And another one is that individual neurons emit periodic signals we will study criticality at the synchronization transition point, which will be a critical point just between synchronization and unsynchronization. So we considered one of the simplest model, the so-called Kuramoto model, which is represented here by these oscillators, edge of the oscillator vectors running through a circle, and the average is just the yellow one. And you can see there, by changing the couplings, there can be different phases. There can be a synchronized phase, a partially this is the synchronized phase, sorry, when the oscillators move together, a partially synchronized state with some outliers, oscillators, and the desynchronized one. And to model it, a common equation is the so-called Kuramoto equation, introduced in 1975, where you have the phases, and you consider the sign of the phase differences between the neighboring sites, and you calculate a weighted sum of these interaction terms. You have in degrees in general for graphs, and you have a global coupling K controlling the phase transition, and you have in general weighted adjacency matrix in. And so this omega E here is just the intrinsic frequency of the oscillators. And you can follow the time evolution of this system by solving this ordinary differential equation and measure the synchronization by the order parameter, which is just the average phase of the oscillators. And this is non-zero above the critical coupling strength when K is greater than Kc, tends to zero if K is less than Kc, as R proportional to the 1 over n squared, where n is the system size. Okay, so finite system, it will have a very small synchronization value, or exhibits an initial growth for incoherent initial state, which exhibit this scale of scaling behavior as a function of n and a function of time. It will grow with the power law just at the critical point. So it is known that critical synchronization transition in the thermodynamic limit can exist only in D larger than 4 spatial dimension, which is a mean field-like behavior, and is corresponding to a full graph. But the dynamical behavior suffers very strong corrections to scaling and chaoticity. And this was our first work, which I don't go into detail, which we just published in GStatMech in collaboration with Robert Juhasz and Jeffrey. This is about high-dimensional mean field systems, dynamical study. I just show you some results for the 2-dimensional lattice of large sizes with periodic boundary conditions with the addition of long links connecting randomly edges such that the average degree will be 5. And in such a big systems, you will have 90 million edges in such systems, and you can follow the growth of the synchronization, this R, starting from a random initial state. And for different coupling parameters on the log-log plot, you can see power law at the criticality or deviations from the power law. And if you also determine the local slopes of these power laws, then you can see the local slopes. Here is a 1 over t, so in the infinite time limit, you can read of the exponents of these power laws here. Okay, I just forgot to mention, so we solved this with this Runge-Kutta-4 parallelized algorithm implemented for GPU by Jeffrey, and we went up to 1,000 time steps and averaged over 10,000 independent omega E realizations. So the critical point is located, and the critical exponent of this is something like 0.55, slightly above from the mean field value from other studies, but this is why we say there is a huge corrections to scaling in the systems. The other thing what we were interested in is the characteristic times. When you start the system from an incoherent state, and these are the single realizations, the order parameter for single realizations, you can see fluctuating a lot, but this is the minimal value for the disorder systems. When they return back and hit the first time, we measure these times, and after performing an average of 10,000 independent realizations, we did the histogramming of these tx times, which can be seen here on this plot. And again, at the critical point, you can see some power law tails, which has a critical exponent at criticality 1.6. So this is interesting for experiments and brain-related studies. But what do we know about neural networks? The largest structural networks contains only 300 neurons, although I heard that the fruit fly has been mapped very recently with some higher number of neurons. Instead of that, we considered large connectomes, which contain 10 to the 6 nodes based on image processing voxels, but these nodes are not really single neurons, but contains already tens of thousands of neurons. And these graphs obtained by DMRA tractography was recently confirmed by tract tracing in case of the ferret. So what we studied, we just took such images, or we don't took it, but those people who published them in the Open Connectome page, which have this 1 millimeter cube resolution and containing up to 1 million nodes. These are hierarchical graphs. The top level are just the 7 brain region coming from the desiccant atlas of the human brain. And the lower levels are determined by these tractographic algorithms. Maps are mapped onto the vertexes, 10 to 7 ones, fibers to edges. And after some noise reduction, one can get a graph which is undirected but weighted. And these graphs can be downloaded from this Open Connectome page. And we have analyzed them earlier with my other collaborator, many of these graphs, and we found that here is the modular structure, for example, this graph. These graphs exhibit small weirdness, but still they are finite dimensional. Their dimensionality is slightly higher than 3 than the embedding space due to the long-range interactions. They are non-scale free, but they exhibit some other stretched exponential distribution, and there are some certain number universally of these graphs. I don't go into the details. I just tell that we took one of these graphs, which is the so-called KK18 graph, which has 836,000 connected nodes and 41 million weighted edges. And we applied this Kuramoto model onto this graph. So again, we try to determine the synchronization transition point, but since the dimension is topological dimension of this graph is less than 4, it's not a real phase, so it cannot be considered. It's a more smeared, it is a crossover point in the sense of thermodynamics. But in this graph, you can see R as a function of t on the log-log scale. Again, some curves veer up, some curves go down, so there is a convex concave inflection point, and you can read of the transition point. Here in this, the lower inset, you can also see the steady state value at the transition point, and in the high inset, you can see the effective exponents of this graph. So, but due to the fact that link weight distribution, we also had to normalize the weights, because otherwise we do not really see transition, but the large hubs, which has the huge weights, dominated the whole network. So this really corresponds like some kind of equilibration in the brain system, some homeostaticity. Okay, so we determine the transition point and the growth exponent. Furthermore, we measure the characteristic times, as was done for this two-dimensional lattice, and after histogramming, we find this kind of duration, desynchronization duration distributions around the transition point, which can be fitted by some power laws, the tails, and the tail exponent tau t is 1.2 obtained, but it seems to be out of range of the experimental value, which is between 0.1 and 2.4 by experimentalist. So we applied another transformation of the graph. We assumed that between 5 and 20% of the nodes are inhibitory, and we flipped certain amount of weights in the graph according to these inhibitory assumptions. We again determined the transition point as before, and desynchronization avalanche distributions. And now we found some exponents which are now inside the experimental range. Furthermore, if you can look at closer, this power law tails seems to have some control parameter dependence. So this suggests that this disorder in the system, this heterogeneity, generates some kind of so-called frustrated synchronization. So let me go to the conclusion. Heterogeneity effects are considered on large human connectomes in case of two-dimensional lattices with long-range interactions, very large sizes. We could study with the help of GPUs. In case of this large human connectome graphs, there is a degree distribution universality, but if we apply the Kuramoto synchronization equation and solve them with this fourth-order Runge-Kutta method, on parallel GPU, we found transition results. So, okay, this goes back to the previous sentence. So in case of 2D, we found some mean field behavior and some corrections to scaling, and we found the characteristic exponents. But in case of the human graphs with normalized weight distribution, the duration exponents are out of the experimental range. On the other hand, when you assume that certain amount of nodes are inhibitory, the characteristic exponent is within the experimental range, and we see some signals of frustrated synchronization subcritically. Okay, so there is some insensitivity to link sign reversal according to these studies. And if you are interested into the details, you can have a look on the archive at the moment. And we also acknowledge support from the Hungarian high-performance infrastructure provided for the academic research. Thank you for your attention.
Any questions? Then I have one. You mentioned that the living creatures where we understand exactly the structure is just a few hundred or a few thousand neurons, but in the human brain we can only measure more coarse-grained, with a more coarse-grained resolution. If in the future we can improve this resolution and get a more complete graph of the brain, would it change these results, or you expect just the power law tail to continue and no new thing appear there?
This is a good question. I mean, we hope that our results will be valid, but we cannot be sure because the large graph we considered describe the white matter tracts, nothing about the gray matter. So if we assume that structurally the white matter and the gray matter are similar, then my answer is yes, but nobody knows at the moment.
Thank you very much. Any more questions? Then let's thank Géza again.